Welcome back, guys. This is our lecture on constant acceleration and free fall. Unit 1 motion. Let's get started. Uh-oh, what's that? Alright, so I barely survived that explosion due to the fact that I benefited from acceleration due to gravity. My speed increased, just like all falling objects have their speed increased due to the force of gravity. Okay, so as a quick recap, now that we're back into lecture mode, acceleration, we said last time, is the rate at which velocity is changing. In fact, the reason I was able to survive that explosion was my velocity at any given time was equal to my initial falling velocity plus the velocity that gained due to acceleration times time. All right, so acceleration equals change in velocity over time. If we manipulate this equation, we can get our first kinematic equation. This equation ends up being very useful. We'll see that we can predict how fast things go and how far things go overall. Other thing we saw previously was the acceleration an object experiences, the change in its velocity over time, is the result of a net force on an object. If we have two teams pulling in tug of war, the object will accelerate, change its motion in the direction of the greater force, right? So, what does that mean for us? Well, as I was falling, the force of gravity was the biggest force on me. In fact, when we talk about falling going forward, and as we saw in class, that we had a bowling ball and a basketball hit the ground at the same time. They tracked each other exactly. We knew they accelerated, and yet neither of them gained speed on the other. So they accelerated with the same rate. But if we took a piece of paper or a feather, well, we had air resistance that kept the feather or piece of paper from hitting the ground at the same time. Going forward, we're going to eliminate the effect of air resistance. We're going to talk about free fall. Free fall is when we have gravity as the only force on the object, no air resistance whatsoever. Okay? Objects that are in free fall increase their velocity at a constant rate that we call the acceleration due to gravity, g. So what's that value? It turns out that the acceleration due to gravity depends on the mass of the Earth and doesn't depend on the mass of the object that's falling towards the Earth. Okay? It also depends on how far away you are from the Earth, which is a term we would call our radius of falling. But for all of our problems, we're going to assume that we're at a constant distance, 1 mile away from the Earth, 2 miles away. In the grand scheme of things, that's not very much. Okay, so the acceleration to gravity near Earth is 9.81. We're going to approximate it as 10 meters per second. So if you're falling near Earth in free fall, no air resistance, you're going to change your speed by approximately 10 meters per second every second. Okay, so let's see what that looks like in action. If I were to take a ball and at t equals 0 seconds, I drop it from rest. That means it has no initial velocity. We can use our equation from above and say that our velocity 1 second later is going to be equal to our acceleration times time. Well, that happens to be our constant value. Acceleration due to gravity, 10 meters per second squared times 1 second. After 1 second of fall with no air resistance, we get a second of speed. Same thing, we say our initial velocity was 0. At t equals 2 seconds, we have 0 plus 10 meters per second squared times 2 seconds, and we get 20 meters per second. So when objects are falling under the influence of gravity and no air resistance, they're in free fall, our objects are changing their speed by 10 meters per second every second. And it follows this equation. All right, pretty cool, right? Predictable, in fact. So, what if we had an object that you threw upward? Say my initial speed, we said velocity equals your initial speed plus the acceleration times time. What if my initial speed was not 0? Say it was 30 meters per second. Well, what happens then? Well, if we're under the influence of gravity, we're still technically in free fall if there's no air resistance, even if we're going upwards. Well, we would have our initial velocity plus our acceleration times time. That would be 30 meters per second plus negative 10 meters per second squared times our time, 1 second. All right, that gives us 20 meters per second. So it's the same thing. Every second when an object is under the influence of gravity, we get a constant change of about 10 meters per second every second. Okay, so t velocity at t equals 2, we'd have 10 meters per second. One last thing to note, we're going to define upwards as a positive direction in physics, downwards as negative. So over here, we have negative velocities. Over here, we have positives. All right, one last thing. At the peak of any trajectory, we have a transition from positive to negative, just like the transition from, on a number scale, from 2, 1, 0, negative 1, negative 2. Whenever you have a change between positives to negatives, you must have a 0. So if we have an object that's going upwards, then downwards, at the peak, velocity is always equal to 0. All right, we made it. No explosion this time. But what's that? Uh-oh.